Hello and welcome to the webinar of Würth Elektronik ISOs. My name is Eleni Stark and I will moderate the webinar today. We are very participate in our webinar, our product manager Jelena Miuskovic and our consultant Jörg Hanschel. They will hold today's webinar on selecting the right coils for wireless power transfer systems and also answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you can't ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You'll find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 15 minutes in addition scheduled for this. If we are unable to answer all your questions within these 15 minutes, please email us at isos-webinar@we-online.com. We will try to answer all your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to optimize our webinars. The link to the recording of today's webinar, as well as the presentation, will be sent to you in a separate email one day after the webinar. You can also watch the recording of today's webinar one day later on our website under the navigation point webinars or on our Würth Elektronik YouTube channel. Now I'm giving directly to our speakers and I wish you an exciting webinar.
Hello, also from our side here, we are very happy to give you some insights on two coils for wireless power transfer. My name is Jörg Hanschel. I'm working currently as a consultant. I worked for Würth in the wireless power field for several years, but now I'm in retirement. But nevertheless do this stuff and, for example, also doing the standardization in the wireless power consortium. And with me is my colleague Jelena.
All from my side, my name is Jelena Miuskovic, and I work as a product manager in wireless power transfer team. As a product manager, I'm responsible for our wireless power coil product line that we have in our portfolio, but also I'm working on customer-specific projects, which means supporting our customers and integrating wireless power in their designs. So in the next half an hour, we would like to give you, as Jörg mentioned, some insights in how to choose the optimized coil for your wireless power application. At the beginning, we would like to give you an overview of potential wireless power applications, then move to basic technologies, wireless power technologies, then discuss about design specific consideration from coil perspective, then give you an overview of wireless power market, and conclude with Würth Elektronik products and advantages.
Okay, then before we talk about the applications, I think we should mention what gave the last really huge push for wireless power in the consumer field. This is from last September, the decision from Apple to integrate wireless power from the iPhone 8 and iPhone X onwards in all their smartphones, and using for that the G standard of the WPC. So this really, let me say, changed the world due to the fact that the last big player who hasn't decided also joined the club in the smartphone field, so that now in principle all major smartphone companies have wireless power according to the G standard integrated in their phones. Applications. So besides the consumer products, there are several areas where wireless power is very beneficial. Automotive is one of those. Charging smartphones in the cars you can, for example, in Europe, choose 40 cars where you can, let me say, a wireless power charging function for your smartphone when you order your car, but also charging an EV wirelessly is starting. So I think this year Mercedes-Benz will bring an hybrid or an EV with integrated wireless power charging, and then it's we are talking about, for example, 6 to 12 kilowatts. Another point related to charging smartphones is furniture and infrastructure. So, for example, table charging possibilities in hotels, in restaurants, in airports, in all these public places is an area where the technology is very beneficial. A field where we see a lot of interest for wireless power is medical. We have a lot of medical projects ongoing. Especially beneficial is here that with wireless power you get rid of charging contacts, which are very difficult in sanitation of medical devices. So with integration of wireless power, you can completely seal those devices and have an easy cleaning and sanitation method available. And the same is for industrial, in harsh environments, in dirty environments, underwater, or in explosive areas. You get rid of charging contacts. You can totally seal products when you are using wireless power, and not only for charging, but also for really using the energy directly in the devices. And a last application area I would like to mention is kitchen, back in the consumer field. Especially why a cordless kitchen. We have a lot of corded devices like blenders, toasters, coffee makers, kettles, pans from different suppliers. And imagine you have these red spots where you always put the device you would like to use on that, and it works there. This is also not charging, but directly using the energy there. So if you put a kettle there, then you have 1.5 kilowatts, for example, in that area. And here a project in the WPC is going on to make an interoperability standard for the cordless kitchen.
Okay, let us move to technologies and standards. So wireless power transfer can be categorized into inductive power transfer and resonant power transfer. Inductive power transfer, basically with this technology, the energy is being transferred from a transmitter coil to receiver coil over magnetic field. This is a closely coupled solution. The distance between two coils is typically up to 10 millimeters, and let's say this technology operates at frequency range from 100 to 200 kilohertz. On the other side, resonant power transfer allows the possibility to charge multiple devices at the same time, and the distance between the coils is possible up to 40 to 50 millimeters. But when it comes to this technology, the compromise or drawbacks of this technology is lower efficiency compared to inductive power transfer. Here we see two application examples from these two main technologies. So on the left side, you see inductive power transfer, and on the right side you see resonant power transfer. So inductive power transfer is currently the mostly widely adopted technology mostly, let's say, due to its high efficiency. But on the other side, this technology requires precise alignment of the two coils. When it comes to resonant power technology, let's say this requirement is not that stiff. It is possible to charge more devices at the same time. On this particular example, 3. But the drawbacks are, as mentioned, lower efficiency, greater circuit complexity, and potential EMI challenges and safety regulation challenges as well. Okay, so when integrating wireless power transfer coils into your wireless power transfer systems, there are several parameters that needs to be taken into considerations, such as power level. So what power I would like to transfer. If I want to, what power I would like to transfer, and if I want to, let's say, comply to some standards like the lead-in-chief standard, freedom of position in receiving device, then distance between a transmitter and receiver coil. So over what distance I would like to transfer this energy? Do I have a limited space within my receiving device, which will affect my choice of receiver coil? Electrical performance, do I have something? Do I have some upfront decided parameters such as RDC, inductance, and others? And finally, price. Two main components of wireless power transfer systems are the coils and chipsets. And there are, as you can see, several chipset suppliers in the market, such as Texas Instruments, IDT, ROHM, NXP, ST Micro, and others. All these chipset suppliers comply to G standard, but they, let's say, differentiate in size, power classes, number of external components chipset have, let's say, additional features such as power management, battery management, data communication, and others. However, whatever chipsets you decide to use, all our coils are referenced and with these chipset suppliers and integrated into their design kits and evaluation boards. When you have further questions about chipsets, you can directly contact these guys. Freedom of positioning. Freedom of positioning refers to the, let's say, flexibility of movement of receiver coil. What that exactly means, I will try to explain on this example. On these 3 pictures, we can see 3 different types of transmitter coils. Single coil on the left side, in the middle is 3-coil array, and on the right side is multiple coil array. In the case that we decide that our receiving device will be fixed in one position, then a single transmitter coil would be the most appropriate and, let's say, the most the best, let's say, the cheapest solution. Then, in the case that we want our receiving device to be flexible in one direction, so X or epsilon direction, then would be recommended to use 3-coil array. And if we want flexibility in both X and Y direction, then we recommend to use this multiple coil array. Coupling between 2 coils depends on alignment, so placement of 2 coils in X and Z direction. There are 3 types of misalignment. We have lateral, angular, and vertical misalignment. And angular misalignment are the most detrimental sort. In order to see the effect of angular misalignment on the coupling factor, we did a simulation with our magnetic field analysis tool to see the effect of 40 degrees angular misalignment on the coupling factor. On this graphic, on the right side, you can see dependency between coupling factor and vertical displacement in degrees. So we can conclude that the coupling factor, so the 40 degrees angular misalignment reduces the coupling factor from around 0.9 up to 0.4, which means that this is basically more than 50% lost of efficiency of the between two coils. Next very important parameter that needs to be taken into consideration is size ratio between two coils. Coupling factor depends also on the size ratio between two coils. In this example, here we see one transmitter coil and 3 receiver coils. In the case, all these 3 receiver coils would work well with this transmitter coil as the size ratio goes to 1:1 to up to 2. Coupling factor drops, but this coil combination will still work well with this transmitter coil. On the other side, if the size ratio between two coils goes to up to 1:6, then we have a significant drop in the coupling factor. But most importantly, the receiving coil wouldn't be recognized by transmitter coils as the active area of the receiver coil is too small. In the case that we are not, we are let's say limited by the size of the receiving coil, one solution that will be good, appropriate for us is to take a smaller transmitter coil that has the same inductance value like the big coil on the big transmitter coil on the left side, and then achieve a much higher coupling factor, and this system of these two coils would work perfectly well.
This is an example. Sorry, this is an example from the iPhone 8, and which shows that Apple did their homework by implementing the right coil. You see, this is a very huge receiver coil. So with this coil, they made sure that they always get this 1:1 size ratio between the transmitter coil, which is given by the standard, by the G standard, and their receiver coil here. So they ensured here to have the best end user experience in by using this big coil, only to show, to demonstrate what the impact could be to use or to spend the area for the coil.
Also, one of the important parameter is magnetic field pattern. So on all the coils we offer in our portfolio, we have our ferrite shielding. Ferrite shielding is very important because it has direct influence on the coupling between two coils, also increases the inductance of the coils, and finally protects from the unwanted emissions in the environment. And on these 3 pictures, for first one, where you see without the shielding, this is the let's say air coil without the shielding, and you can see the magnetic field is going everywhere in the environment. Below this picture, you can see coil with shielding, where you can see the magnetic field is concentrated and doesn't go below the ferrite shield. And finally, the picture on the right side shows a magnetic field between two coils, both with ferrite shielding. And from this picture, we can conclude that the magnetic field is concentrated between two coils. We have heard, let's say, we have learned from the previous slides the importance of the coupling factor. But let's say if the coupling factor is reduced by the misalignment, one of the parameters that we can increase the efficiency of the system is with the quality factor of the coil. Quality factor is influenced by the size and the shape of the coil, but more importantly, the ferrite material used. And the ferrite material with high permeability and low losses can significantly increase quality factor. These two examples of these two coils is a good example to see how magnet influences the quality factor. On the left side, we can see A1G coil that has magnets inside, so in the middle, and on the right side is the A10G coil that doesn't have the magnets, and we can see that quality factor is almost doubled, not almost doubled, when there is no magnet inside.
The coupling factor and the efficiency are, let me say, key parameters for a wireless power system. And based on the stuff you just heard, we would like to, let me say, combine the information so that we face in, let me say, all wireless power systems a certain loss factor, and we have a certain efficiency, means the energy transmitted compared to the energy transferred. And these parameters you can influence with the coil, with choosing the right coils. So the coupling factor learned is influenced by the positioning of the coil. So if you, when you are designing your system, if you take care that your receiver coil is always placed properly on your transmitter coil, then you influence the coupling factor positively. And the other point with the Q factor is influenced by the performance of the coil. So means if you have a high performance coil with very good ferrite material, with high performance Litz wire, then you get, let me say, additional performance in your overall system. So this you should always keep in mind when you are designing and choosing the coils. Now let's for a moment leave the more G standard related stuff. Also, if you, for example, are planning or you need to transfer an energy up to 200 watt, Würth Elektronik can help you. We have an application note on our website with up to 200 watt solutions where we can provide you BOM, layout, Gerber files, all the relevant stuff so that you can build up or integrate this into your system. The demonstrator looks like that. We have a 60 watt demonstrator on that. It's a resonant converter, so you can use the same board as transmitter and as a receiver. The important point here regarding the coils is you can see that we are using the same coil as transmitter and as receiver due to the facts we just mentioned, that here we really make sure that you have a high efficiency, a good coupling, and a good energy transfer. Then when you have integrated wireless power successfully in your device, then you have a last step to take into consideration. This means approval. For the approval, there are, let me say, for example, if you are choosing a G solution, there are two things to keep in mind. The official mandatory regulatory tests, so they are mandatory by country region to being allowed to bring a device to the market. So means FCC in the US or the RED directive or the so-called radio approval in Europe. So for wireless power systems where you have energy and data, even if the data is only related to the power management, doesn't matter. If you transfer the data via the coils during the energy transfer, you have to make a radio approval according to the RAD regulatory requirement. If you are using the G chipset or the G system without needing the interoperability, then you are done with the RED directive with the radio approval. But if you would like to choose, for example, if you are developing a transmitter for charging smartphones, then we strongly recommend also to make a G certification, but this is not mandatory. This is a so-called private requirement due to the fact that the WPC is a voluntary, let me say, a consortium of more than 400 companies, and they define the standard, they define the approval tests, and they are also, let me say, defining which approval labs you have to get your G certification. But this is really only needed if you would like to have this interoperability. You can use the G chipset, the G coils, but you don't need to have a G certification if not needed.
Let's have a short overview about the wireless power transfer market. So as we can see from this graphic, in the next decade, wireless power transfer market will continue to gain widespread adoption across many different application areas. But let's say consumer market is still expected to be the main driver. When it comes to receiver shipments, they are going to continue to grow rapidly, with let's say more than 1 billion receiver shipments by 2020 and more than 2 billion receiver shipments by 2025. And let's say transmitter shipments will follow this growth, but in a steadier pace. When it comes to wireless power, Würth Elektronik wireless power products, so by this year we have more than 50 transmitter and receiver coils in our portfolio. We have also G compliant coils that are usable up to 20 watts, and also if you, as Jörg mentioned, are not following the standards, then we have also available portfolio for higher power. So yeah, we try to cover from the lower power up to higher power range. When it comes to customer-specific coils, we get a lot of questions. Are we doing this? Actually, yes, we are working on customer-specific projects. The MOQ for such projects is about 5,000. And if you have a question or you have, let's say, the exact design that you would like to have, please use sheet that you can find on our website, or you can contact your local sales that will help you with your request.
And to help you getting started with wireless power, we also offer a demo kit and ready-to-go solution with G 15 watt, the current available version. Here you have the possibility, for example, to connect your device with the receiver, make some inquiries and checks if it works, and with wireless power in an easy way. You can also, due to the fact that, like Jelena mentioned, we are talking about frequency ranges from 100 to 200 kilohertz, does the wireless power transfer influence some other components in your device? So this is a really development environment what you can use to get an easy, fast start. And this is an available kit also online and with our sales guys. What else can Würth Elektronik offer you? We have a lot of material on our website, which has, for example, the inquiry sheet for the customer calls and a lot of additional beneficial material. And a very important point, especially for G solutions, is our mix and match table, which we would like to show you. We are quite proud on that because we won an innovation award last year for passive components with a software, which is also quite nice. The purpose of this is, we spend a hell of effort on that, is to give you a guidance to choose the right coil or the optimal coil combination for a G solution. So in all the lines you see all transmitter coils we have, and in on the columns you see the receiver coils, and where there is a green dot, this is a combination which works perfectly, so you can without any hesitation take this coil combination. If there is a red dot, don't even try it, it will not work. We tried it. Or the reason mainly is that, for example, like said before, the coil area ratio is not fitting, so it will not work. If there's a yellow dot, it might work with some restrictions. In that case, if you need, for example, from space limitations, if you need this coil combination, ask us and we can give you some guidance. Then if you click on one of those green dots, you will guide it to our Red Expert, which is our famous tool for all our components. And then you are in the wireless power section. And here the important information, besides additional parameters, is this box on the left side, which shows you the capacitor values in the resonant tank of the receiver. The point of that is we did this due to the fact that a lot of customers said, okay, we took the reference design from Texas Instruments or IDT, and it doesn't work properly, the coils get hot, and then we ask normally, have you adopted or adjusted the capacitor values in the resonant tank? And then the customer normally said, oh, have I to do this? Yes, you have to do this because in the reference design of the chipset suppliers, they are using one coil, one dedicated coil with a certain characteristic. And if you are choosing a different coil, then you have to adjust the values of the serial and parallel capacitors in the resonant tank on the receiver side. And here you can find in this Red Expert those values. So this is a very important additional support we can give you to make a successful G implementation in your device. Yeah, this was it. So for the summary, what we would like to highlight is the overall system performance depends really on the coil placement as learned, and the coil performance. So here you can do a lot of things right or wrong. And especially when the interoperability is not needed, you can optimize with the coil combination the performance of your system. I give you an example. In the G standard, the maximum distance between the coils is limited to around 8 millimeters. So if you have a distance of, for example, 12 millimeter between the transmitter and receiver coil, you can reach this with choosing the right coils out of our spectrum. Then you can achieve your goal and optimize your performance. You might not get a G certification, but if you don't need the G certification, it doesn't matter. You get your problem solved that you can transfer the energy over 12 millimeters. So this is meant by that. And with that, we thank you for your interest and are now going to answer your questions.
Okay.
So let's. Okay, question. What about metal near a wireless power system? Very good question. What about metal? Yeah, metal in between transmitter and receiver coil is an absolute no-go because you get eddy currents in, it heats up the metal. So this will not work. So also a metal housing will not work. But if you cut out an area in your house, in your metal housing, to give the transmitter or receiver coil a free side to the corresponding coil, and leave, let me say, a certain area of 5 to 7 millimeters free, then it will also work with a metal housing. But the point is no metal in between. For example, in the G standard, there is the so-called foreign object detection integrated, where the system detects metal if there is accidentally metal in between the transmitter and receiver coils, and then a security feature shuts off the energy transfer. Okay. Then what is the maximum Z distance? It depends on, so the distance, as said in a G system, is limited to, officially in the standard, to 2 to 8 millimeters. You can, as just mentioned, you can extend this, but then you are outside. It will work, but you are outside the G specification. If you are going for a proprietary solution, like I showed you with this 200-watt solution, then you can also reach 40 millimeters, 50 millimeters. The drawback is you lose efficiency, like we also showed that this is the price you have to pay. But if it's important for you to cover this distance, you can reach it, but have then to accept the losses. Okay, last questions. What about safety or impact of humans near wireless power system, so especially pacemakers? Good question. Point is, in a, let me say, inductive solution, you have the magnetic field, like Jelena explained, is quite limited between the coils and is shielded with the ferrite shielding. So all the G system and all the systems comply to all the SIR and other requirements, safety, security features. So this is not seen critical. Nevertheless, you should not keep it directly in direct contact. So, but this is in, let me say, resonant solutions, it's a little bit more tricky due to the fact that there is, with the higher spatial freedom, there is still some risk in that some of the field is not directly under control, but in principle, all commercial systems, this is the good news, are safe on that. Now we have another question. What is the ideal frequency of operation? Nice question. It depends on. You cannot use you have to have a frequency range where it is allowed to transfer energy from the approval point of view. So the commercial systems like G work in this 100 to 200 kilohertz solution. The Air-Fuel Alliance standard, which is a resonance standard, operates at 6.78 megahertz. This is also an ISM band where energy transfer is allowed. The, let me say, higher energy charging of electrical vehicles, 50 and 100 kilohertz. So this is the area. There is no ideal frequency. You have in your system to tune your transmitter and receiver to that frequency, and then you get the most efficient transfer. Okay, so these were the questions, and I think we are perfectly in time. With that, we thank you very much for your interest. Wish you a nice rest of the day. And if there are any questions coming up later, just let us know. Thank you very much. And with that, we end the webinar.
Thank you. Goodbye.